300 miles off the Oregon coast, on the floor of the Pacific Ocean, a volcano the size of Hawaii is waking up. Pressure readings at Axial Seamount have just shattered every record scientists have collected in 30 years of continuous monitoring, and the seafloor itself has inflated to levels that preceded the last 3 eruptions. Seismometers are screaming. The magma chamber is filling faster than any model predicted. And what happens next on this single underwater volcano could trigger a chain of consequences that reaches from the ocean floor all the way to the coast of the Pacific Northwest. March 2nd, 2026. Scientists at the University of Washington's Pacific Northwest Seismic Network stare at data feeds that should not exist. Overnight, seismic monitoring arrays anchored to the seafloor at Axial Seamount registered 1,400 individual earthquake events in a single 12-hour window. Not 1,400 over a week. Not 1,400 over a month. 1,400 in half a day. The Ocean Observatory's Initiative Cabled Array, the most sophisticated underwater volcanic monitoring system ever built, begins transmitting numbers that send researchers scrambling from their chairs. Bottom pressure recorders planted directly on the summit caldera detect uplift measuring 41 centimeters above the 2023 baseline. 41 centimeters of inflation in the caldera floor. The seafloor is rising. The magma chamber beneath it is filling, and it is filling fast. Hydrothermal vent temperatures along the caldera rim spike by 22 degrees Celsius in less than 18 hours. Instruments designed to detect gradual geological change are instead capturing something violent and accelerating. Chemical sensors deployed across the vent fields register sulfur dioxide concentrations, climbing at rates that oceanographers describe as extraordinary. The water column above the caldera darkens with particulate matter rising from the seafloor. The ocean itself is reacting. Emergency scientific coordination calls activate across multiple institutions simultaneously. The National Oceanic and Atmospheric Administration convenes an UN-scheduled briefing. Oregon State University volcanologists cancel fieldwork to monitor incoming telemetry. The Woods Hole. Oceanographic Institution flags the event for immediate international review. The numbers are already historic. The seismic swarm has not paused. The inflation has not reversed. The pressure has not released. And every instrument on the seafloor is pointing toward the same conclusion. Axial Seamount is not showing early warning signs of possible future activity. Axial Seamount is already in eruption, and no one on the surface knew it was coming. To understand why scientists are in a state of controlled panic, you have to understand what Axial Seamount actually is. This is not a minor underwater ridge. It is not a geological footnote sitting quietly on the ocean floor. This is one of the most volcanically active structures on the planet. It sits 300 miles off the Oregon coast, at a depth of 1,500 meters beneath the Pacific Ocean. Axial Seamount rises nearly 1,000 meters from the surrounding seafloor. Its summit caldera measures 3 kilometers by 8 kilometers. A massive collapsed volcanic depression riddled with hydrothermal vents, lava fields, and fracture zones that have been erupting, recovering, and erupting again for hundreds of thousands of years. It sits directly on the Juan de Fuca Ridge, the tectonic boundary where the Pacific Plate and the Juan de Fuca Plate are actively spreading apart, pulling the seafloor in opposite directions and feeding a magma supply that never fully stops. The volcano erupted in 1998. It erupted again in 2011. It erupted a third time in 2015. Each eruption was preceded by the same recognizable sequence. The caldera floor inflated as the magma chamber filled. Seismic activity intensified. Seafloor pressure sensors registered accelerating uplift. Then the eruption came. Lava poured across the caldera floor. The inflation reversed, and scientists reset their clocks and waited for the cycle to begin again. After the 2015 eruption, the caldera floor dropped by over 2 meters as magma evacuated from the chamber. Since that moment, the floor has been rising, slowly at first, then faster. Now, on March 2nd, 2026, the inflation has exceeded the pre-eruption threshold recorded before every previous event in the modern monitoring record. The volcano has done this before. The difference this time is the speed. The difference this time is the pressure. And the difference this time is what scientists are finding buried in the data that no one is talking about publicly. Dr. William Chadwick, research professor at Oregon State University and one of the world's leading authorities on axial seamount, has monitored this volcano through 3 eruption cycles. He helped develop the inflation threshold model that successfully predicted the 2015 eruption months in advance. When colleagues ask him to compare current readings to anything in the 30-year observational record, he pauses before answering. The bottom pressure recorder data is the first signal that breaks from the historical pattern. In the months preceding the 2015 eruption, caldera inflation reached approximately 2.4 meters above the post-eruption baseline before the event triggered. Current measurements on March 2, 2026 show inflation at 2.7 meters above the 2015 post-eruption floor. The threshold that has preceded every recorded eruption has not just been reached. It has been exceeded by 13%, and the floor is still rising. The seismic signature carries its own disturbing message. Earthquake swarms at Axial Seamount are expected. The volcano generates thousands of small magnitude events annually as magma moves and rock fractures under pressure. But the character of the current swarm is different from anything in the database. Seismologists at the Pacific Northwest Seismic Network identify harmonic tremor signals embedded within the swarm data. Harmonic tremor is not random rock fracturing. Harmonic tremor is the resonant vibration of fluid, specifically magma or volcanic gases, moving through conduits under pressure. It is the sound of the volcano's plumbing system activating. The hydrothermal vent temperature data compounds the alarm. Axial Seamount hosts one of the most extensive hydrothermal vent ecosystems in the Pacific, and those vents serve as direct thermal indicators of what the magma chamber below that is doing. Vent field temperatures measured across the caldera summit on March 1st registered an average increase of 31 degrees Celsius above the 6-month baseline. In the 48 hours before the 2015 eruption, vent temperatures rose by 19 degrees. The current increase is 63% higher than the pre-eruption signature from the last event. Chemical monitoring stations detect elevated hydrogen sulfide and methane concentrations rising through the water column above the caldera. The ocean chemistry above the volcano is changing. Dissolved mineral concentrations in the hydrothermal plume have doubled since January. Microbial mat growth along the caldera rim, which expands in response to increased thermal and chemical output, has accelerated at rates that marine biologists describe as exceptional and alarming. Every instrument, every data stream, every chemical indicator, all pointing in the same direction, all saying the same thing. The pressure inside Axial Seamount has gone through the roof, and the roof is beginning to crack. The story of what is happening at Axial Seamount did not begin in March 2026. It began in the summer of 2024, and the progression follows a trajectory that volcanologists recognize with cold familiarity. June 2024. NOAA ocean buoy arrays detect the first statistical anomaly in seafloor pressure readings above the axial caldera. The deviation is small, within noise parameters that monitoring algorithms typically filter. One researcher at the University of Washington flags it in an internal memo. The memo is noted and filed. September 2024. The Ocean Observatory's initiative, cabled array, transmits updated uplift measurements showing cumulative caldera inflation of 31 centimeters above the post-eruption 2015 baseline. A research team at Oregon State University publishes a brief technical update in a scientific journal noting that inflation rates appear to be accelerating beyond the pace recorded in the years following the 2015 event. The paper receives attention within the volcanological community. It receives almost none outside it. December 2024. Seismic event frequency at Axial Seamount increases by 240% compared to the same period in 2023. Earthquake swarms that previously produced 40 to 60 detectable events per week begin producing 150 to 200. The Pacific Northwest Seismic Network upgrades monitoring frequency and begins continuous human review of incoming data. February 2026. The escalation leaves the realm of gradual trend and enters something else entirely. In the first 28 days of February alone, Axial Seamount generates 11,840 documented seismic events. Harmonic tremor sequences appear in the data on 14 separate occasions. Bottom pressure recorders register the largest single-week inflation measurement in the 30-year observational record. Vent temperatures begin their rapid climb. February 27, 2026. 3 days before the current crisis reaches full alert status, NOAA internal communications flagged the combined data picture as requiring immediate escalation to agency leadership. The phrase used in the internal briefing document, obtained by research institutions monitoring the situation, describes the convergence of signals as unlike anything in the historical baseline for this system. March 2, 2026. The seismic swarm exceeds 1,400 events in 12 hours. The caldera floor registers 41 centimeters of uplift above the 2023 baseline. And the instruments that have predicted every eruption at this volcano for 30 years are all screaming the same warning at the same time. 300 miles of open Pacific Ocean separate Axial Seamount from the Oregon coast. That distance might suggest insulation, a comfortable buffer between an erupting underwater volcano and the millions of people living in Portland, Seattle, Eugene, and the coastal communities of the Pacific Northwest. Scientists studying the full implications of this event are not comfortable about that distance. Not even slightly. The ocean above Axial Seamount is not empty. The Juan de Fuca Ridge corridor supports one of the most ecologically significant marine environments in the Northeast Pacific. Axial Seamount itself hosts extraordinary biodiversity clustered around its hydrothermal vent systems. Tube worm colonies, giant clam beds, unique microbial ecosystems found nowhere else on Earth. When the volcano erupts, lava flows across the caldera floor and buries these communities under meters of fresh basalt. The 2015 eruption entombed an estimated 300 million tube worms in a single event. But the ecological stakes extend far beyond the caldera. The Northeast Pacific commercial fishing industry operates across the waters above and around the Juan de Fuca Ridge. Pacific salmon migration routes pass through the region. Tuna, halibut, and Dungeness crab fisheries worth billions of dollars annually depend on the health of this marine ecosystem. A major eruption at Axial Seamount does not only transform the seafloor, it generates hydrothermal plumes that rise hundreds of meters into the water column, altering ocean chemistry, affecting pH levels, and introducing mineral concentrations that disrupt the food chain from microscopic plankton upward. Oregon and Washington commercial fishing fleets are watching this situation with the specific and focused attention of people whose livelihoods depend on what happens next. The ocean is not a barrier between this volcano and the surface world. The ocean is the connection. Here is what has geologists in complete panic, and here is what no official briefing has stated plainly enough for the public to grasp. Axial Seamount does not sit in geological isolation. It sits on the Juan de Fuca Ridge, which feeds directly into one of the most dangerous tectonic boundaries on the planet, the Cascadia subduction zone. The fault system runs from northern California to southern British Columbia. It is capable of producing a magnitude 9.0 or greater megaquake, the kind of event the Pacific Northwest has not experienced in recorded history. but that geological evidence confirms happens on a repeating cycle. The last full rupture of the Cascadia subduction zone occurred on January 26, 1700. It generated a tsunami that struck the coast of Japan. Scientists estimate the next full rupture carries a 1 in 3 chance of occurring within the next 50 years. Axial Seamount sits at the northern end of the Juan de Fuca Plate, the same tectonic microplate that is being driven beneath the North American continent at the Cascadia subduction zone. Every movement of the Juan de Fuca Plate is a movement connected to the subduction system. Every shift in pressure along the Juan de Fuca Ridge affects stress loading on the fault system to the east. Does an eruption at Axial Seamount directly trigger a Cascadia earthquake? Scientists are careful here. The relationship between ridge volcanism and subduction zone seismicity is not fully understood. The data connecting Juan de Fuca Ridge activity to Cascadia fault behavior exists, is peer-reviewed, and is actively debated. What is not debated is the physical reality that these systems share a plate. What happens on the ridge does not stay on the ridge. Dr. Harold Tobin, director of the Pacific Northwest Seismic Network, addressed the subduction zone question in a 2025 interview. He described the Cascadia subduction zone as a locked fault accumulating stress continuously, a system where the question is not if, but when. He described Axial Seamount as the most active and best monitored volcanic system on the Juan de Fuca Plate. He declined to draw a direct causal link between the two, but he also declined very deliberately to say they are unconnected. In emergency planning offices across Oregon and Washington, that careful non-denial is being read with full attention. The Cascadia subduction zone was already the Pacific Northwest's most feared geological threat before March 2, 2026. It has not become less frightening since. Portland, Oregon, population 650,000. Seattle, Washington, population 750,000. The combined metropolitan population of the Pacific Northwest corridor from Eugene to Vancouver, British Columbia, exceeds 9 million people. Every one of them lives within the potential impact zone of a Cascadia subduction zone rupture. Every one of them depends on infrastructure, supply chains, and communication networks that emergency planners have repeatedly warned are catastrophically unprepared for a major seismic event. The economic architecture of the Pacific Northwest is built on coastal foundations that a major tsunami would reach within 15 to 30 minutes of a subduction zone rupture. The Port of Portland, the Port of Seattle, the Port of Tacoma. Combined, these facilities process over $100 billion in trade annually. They sit at sea level. Tsunami inundation models show water reaching inland 2 to 3 miles in coastal communities. Coastal towns of Oregon and Washington, places like Seaside, Cannon Beach, Newport, and Astoria face the most direct exposure. FEMA published a Cascadia subduction zone impact study that projected 13,000 deaths, 27,000 injuries, and 1 million people displaced in a worst-case full rupture scenario. Infrastructure restoration timelines are measured not in weeks, but in years. That study was conducted before the current escalation at Axial Seamount. It was conducted when Cascadia felt like a distant probability rather than an active question. The fishing industry alone, already watching vent temperature data and ocean chemistry readings above Axial Seamount, faces the prospect of indefinite closures across some of the richest fishing grounds in the Pacific. Insurance underwriters in Seattle and Portland are already requesting updated geological risk assessments. The economic machinery of the Pacific Northwest is processing what the seismic data is saying, and what it is saying is not reassuring. Scientists at Oregon State University, the University of Washington, and NOAA are modeling 3 trajectories for the Axial Seamount situation as of March 2, 2026. The first scenario mirrors the 2015 eruption. It would be a relatively contained lava effusion across the caldera floor. Seismic activity peaks and then subsides over days to weeks. Seafloor inflation reverses as the magma chamber empties. Vent temperatures spike during active eruption, then gradually normalize. The scientific community responds with intensive data collection. Fishing fleets experience minimal direct disruption. The event remains, in practical terms, invisible to the public. Most people learn about it weeks later through a science news brief. Life on the surface continues undisturbed. The second scenario describes a larger eruption than the three previous modern events combined. The magma volume currently inferred from inflation measurements exceeds the estimated volume released in 2015 by a factor of 1.8. If that magma reaches the surface through multiple vent points simultaneously, the eruption could produce lava flows covering a significantly larger portion of the caldera floor, generate a more substantial hydrothermal plume affecting a wider section of the water column, and trigger secondary seismic events along adjacent ridge segments. The third scenario is the one that emergency planners across the Pacific Northwest are not saying out loud in public briefings, but are running simulations for in closed rooms. A major caldera collapse event at Axial Seamount, driven by rapid evacuation of the magma chamber, could generate a submarine landslide. Submarine landslides generate tsunamis. The Juan de Fuca Ridge has produced submarine mass failure events before. The geological record shows them. The amount of unstable material sitting on the elevated flanks of a volcano that has been inflating for nearly a decade is a number that submarine landslide researchers are currently calculating with urgent and focused attention. 1 week after the seismic swarm crossed 1,400 events in 12 hours, Axial Seamount has not gone quiet. The instruments have not settled. The inflation curve has not reversed. The harmonic tremor sequences have not stopped appearing in the data. Everything that monitoring science says should precede an eruption at this volcano is present, is active, and is intensifying. The Ocean Observatory's initiative cabled array continues transmitting in real time. Every 6 seconds, bottom pressure recorders update their readings. Every minute, seismometers log the ongoing fracturing of rock under magmatic pressure. Every hour, chemical sensors sample the water column rising above the caldera. The data does not sleep. The data does not pause. And the data continues to say the same thing it has been saying since February 27th. The pressure is still building. What the data cannot say is when. Volcanic science has made extraordinary progress in the 30 years since instruments were first placed on Axial Seamount's caldera floor. Researchers successfully predicted the 2015 eruption. They accurately forecast that the volcano would erupt within a 12-month window, and they were right. But prediction is not precision. Eruptions do not follow clocks. The pressure accumulates until it does not. And the moment of release answers to geology, not to human schedules or emergency planning timelines. The broader question that the Axial Seamount situation has forced into focus is not about one underwater volcano 300 miles off the Oregon coast. The broader question is about the Pacific Northwest's relationship with the geological reality beneath its feet. The Cascadia subduction zone was already there before this week. The Juan de Fuca plate was already locked and loading before the seismic swarms began. The coastal communities of Oregon and Washington were already sitting in tsunami inundation zones before the first harmonic tremor signature appeared in the monitoring data. What Axial Seamount has done is make that reality impossible to look away from. It has placed a seismometer in the public consciousness and told 9 million people in the Pacific Northwest that the geological system they live on is active, is energized, and is doing things that the scientists who know it best describe as unprecedented in the observational record. The seafloor is rising. The magma is moving. The instruments are screaming. And 300 miles off the Oregon coast, at the bottom of the Pacific Ocean, a volcano the size of Hawaii is making a decision that no scientist, no model, and no emergency plan can make for it. The pressure has gone through the roof. The only question left is what comes through the roof next.